So we were talking about shell lengths of sea turtles, and we have a study of green sea turtles inhabiting the Grand Cayman South Sound Lagoon, and we've looked at them before. Researchers discovered that the curved shell length of these turtles is approximately normally distributed, that's important for us to know, with a mean of 55.7 centimeters and a standard deviation of 11.5 centimeters. So for the population, I know the mean is 55.7 and the standard deviation is 11.5. Okay, the minimum and maximum size limits for captured turtles in the legal marine turtle fishery are 40 centimeters and 60 centimeters respectively. So for any turtle that we catch, we want it to be between 40 and 60 centimeters. And remember, it doesn't matter if we put less than or if we put less than or equal. It won't make any difference on our results. So how likely are you to capture a green sea turtle that's considered illegal? So if we're looking at illegal turtles, we're going to have to find the region where they're legal sized and then look at the two outside ends and see where those are. So first thing we want to do is look at if x equals 40, what is my z going to be? And remember our z formula, turn to my blue, z equals x minus the mean over the standard deviation. So for the x equals 40, the minimum size, we would do z equals, plug in that 40, plug in the mu, so 55.7 over the 11.5, and then when I calculate that, 40 minus 55.7, and then do the division 11.5, I end up with negative 1.37. Now that's a value for z, so I can put it down here on my picture. That's negative 1. It's about right here, negative 1.37. And I am considering turtles outside of that interval, so the ones off to this side. And then let's look at our other endpoint, which was x equals 60 centimeters. And then we want to find our corresponding z. So z is going to be 60 minus 55.7, that was our mu, over 11.5. And go ahead and subtract those and then divide by the 11.5, and I get a z of 0.37. So when I come to my chart, 0.37 is about a little over a third of the way between 0 and 1, and then remember I'm talking about those that fall outside of the legal limits, so I want this region here. Okay, when I look these up on the chart, I am going to be looking up this piece, and I really want the other piece, the right hand part here. So I'll have to do 0.5 minus whatever my table lookup is for 0.37. I'm looking at my table here, and this piece here is 0.1443. And I'll do the other one while I'm at it, the negative 1.37, and that's going to be that'll give me this piece here, so that's 0.4147. Okay, so for the right-hand side, the shaded part is going to be 0.5 minus 0.1443, and then when I calculate that, it helps if I get my calculator out to start with, right? 0.5 minus 0.1443, I get 0.3557, and that's this piece here, 0.3557. And then for the other side, the left-hand side, I'm doing 0.5 minus 0.4147, And there I'm going to get 0.0853, so that's this region, 0.0853, and then adding together my two shaded regions, so I have 0.3557 and 0.0853, add those two together, and I think I get 0.441. Okay, and so that's telling me how likely are you to capture a green sea turtle that's considered illegal. And so I can say for part A, the likelihood of capturing an illegal turtle is 0.441. And that's my answer for part A. Then part B says, what maximum limit L should be set so that only 10% of the turtles captured have shell lengths greater than L? So let's take a look at what that would be like. I'm going to change my pen color so hopefully we can see that. So what we're talking about is some point along here so that all of this is just 10% of our distribution. So we're looking at 0. If we want this piece to be, let's see if I can do this, this piece to be 0.10 or 10%, then the piece that we're actually going to be able to look up is going to be 0.400, and that'll be the area of the piece that we want to look up. Okay, so when you look that up, 0.4, so first thing we'll do is look up 0.4 on the table, and we get z equals 1.28. And that'll give about 10% above the 1.28 and about 90% below. So 1.28 is actually right about there. It's 1.28. And then number 2, plug into the z score formula. Make that look like a z. Okay, so when I plug it into the z-score formula, what I'm doing is finding the actual shell length L that corresponds to z equals 1.28. So I have z equals 1.28, and L is the part I don't know, and the mu is still 55.7, and sigma is still 11.5. So if I plug all those in, I have 1.28 equals L minus 55.7 over 11.5. And then I want to solve that, so I'll multiply both sides by 11.5. .28, I get 14.72 equals L minus 55.7. So we'll add that 55.7 to both sides. And get 70.42 equals L. So that tells me that only 10% of the turtles have a shell length over 70.42, and I believe it was centimeters. Let's double check. Yeah, There it is, centimeters. Okay. 5.49. So this is about the electoral colleges. And during a presidential election, each state is allotted a different number of votes to the Electoral College depending on the population. For example, California is allotted 55 votes, the most, while several states, including the District of Columbia, are allotted 3 votes each, which is the least. When a presidential candidate wins the popular vote in a state, the candidate wins all the Electoral College votes in that state. To become president, a candidate must win 270 of the total 538 votes in the Electoral College. Chance Journal demonstrated the impact of winning California on the presidential election. Assume a candidate wins California's 55 votes. The number of additional Electoral College votes the candidate will win can be approximated by a normal distribution with a mu of, there it is, mu of 21 or 241.5 and sigma of 49.8. If a presidential candidate wins the popular vote in California, what are the chances that he or she will become the next U.S. president? So if there are 270 that the candidate needs, and they've already won 55 from California, then there are 215 votes to get. They still need 215 votes. So first, let's draw a little picture and see what that looks like. So we have we need to figure out where our mark is for they have to get at least that many votes. So we want to find out if my x is 215, what is my z? So z equals, and it's going to be x minus mu, of course, over the standard deviation. When I plug in, I'm going to have 215 that I need to get. The mu that we got was 241.5, and the standard deviation was 49.8. When I calculate that out, I get z equals negative 0.53. So that puts me to the left of center, about halfway between 0 and 1. That'll be negative 0.53, right to there. And I want to get at least that many votes, so that means I can get more, and that would be fine, not a problem. So all the way to the right. So I know the whole right-hand side is 0.5, so I need to find, this was my first step, was find the z. And then my second step is find the probability. So the probability is going to be 0.5 plus the probability that z equals 0.53. And I say 0.53 because when I look it up on the table, I can only look up the positive values. So when I look up the 0.53, I get 2019 plus 0.5, so I'm going to get 0.7019 for the probability of the candidate winning based on them having won California. So I would write that as if the candidate wins California, the probability of becoming president is 0.7019. So their chances are 70%. That's pretty high. So California is the state to win.